Hi everybody, in this video I'm going to go over APEX section 10.3.3, which talks about lenses and mirrors, and specifically about calculations involving them. So this APEX section is not very long, so I'm only going to do one video on it, and I'm only giving you one day to go through the APEX section if you'd prefer to do that. So let's get started. We already talked about with lenses and mirrors, you can figure out some things about the image that they produce by using a ray diagram. So you drew a image and you traced where the rays went, and then you could find out some information about your image, like where it was located, whether it was larger or smaller, etc. There's another way of doing this. And the other way of doing this is by using the thin lens equation. Okay? So the thin lens equation is this. It says 1 over f equals 1 over do plus 1 over di. Okay? So in this equation, we have f is our focal point, which we know is the point where light would converge for that lens or mirror. Do is the distance of your object from the lens or mirror. And di is the distance of the image from the lens or mirror. Okay, so even though this is called the thin lens equation, you can use it for both lenses and mirrors. So what we can do with this is if you know the focal point and you know the distance of the object from your lens or mirror, you can use the thin lens equation to find the distance of the image from the lens or mirror. So that can give you some more information about the image produced. To do that, it's often very useful to rearrange this equation to get di by itself. And if you did that, you would get this equation, di equals do times f divided by do minus f. So all I did was I rearranged this equation. Okay. You could also try to find f, and then you would have the equation do times di over do plus di. Okay, and so these are just rearranged thin lens equations. Okay, so also when we're using the thin lens equation, we need to figure out some things about the signs. So we have this table here. Don't bother to memorize it, just have it handy. APEX also has it on the screen for you. But it tells you when things are going to be positive and when they're going to be negative. So the focal length for mirrors, concave is positive, convex is negative focal length. For lenses, it's the opposite. So concave is negative focal length, convex is positive focal length. Now for do, the object distance is always positive, both for mirrors and lenses. Di, which is that image distance, it's positive when it's a mirror. It's positive for real images, and remember, in a mirror, a real image is in front of the mirror, and it's negative for virtual images, which are behind the mirror. For lenses, di is positive for real images, but remember now, real images for a lens is behind the lens, and it's negative for virtual images, and for a lens, it's in front of the lens. Okay? So we need to use all of this information to solve some problems. There's also something else we can do, and that's calculating magnification. Okay? You might have noticed that if you've ever been to like a fun house, sometimes mirrors magnify your image to be larger. Or if you are in like a gas station or a grocery store, sometimes they have those convex mirrors that make the image smaller so they can see everybody around them. Also, the same thing applies to lenses, right? If you have glasses, it might make it bigger or smaller in your image. So we can calculate exactly how much the image is made bigger or smaller using a magnification equation. So here, magnification is abbreviated M. And our equation is m equals negative di over do. So negative distance of the image from the mirror or lens divided by distance of the object from the mirror or lens. okay? And then from that, we can figure out some things. So if you get an answer where it's greater than 1, like you get 2, that means your image is going to be larger than your object. If you get a less than 1 image, like 0.5, your image is going to be smaller than your object. If when you solve this equation you get a positive magnification value, it means your image is upright. If you have a negative magnification value, that means your image is inverted. So sometimes mirrors produce images that are actually upside down. And we know that is the case if you get a negative M. Okay? So let's take a look at an example problem here. All right. We are going to determine where the image will be located and whether it will be real or virtual. Then we're going to find the magnification and determine if the image will be larger or smaller, upright or inverted. So we have this picture here, and we know this is a convex lens. So let's get started. First thing we want to notice is that our focal point is 25 centimeters. But we have to check, is that positive or negative? So we have a convex lens. Let's go back to our table. For lenses, convex lens is positive F. So we're going to keep that as a positive 25. DO is 15 centimeters. And remember, DO, if we go back to our table, is always positive. Okay? Great. So now we can start using our equation. So we want to figure out the image, so we're going to use the equation DI equals DO times F over DO minus F. So we're going to plug in 15 times 25 divided by 15 minus 25. Put that in a calculator and you would get negative 37.5 centimeters. Okay, now what does this mean? Well, we have a negative value, so we have a negative DI for a lens. Let's see what that means. Go back to your table. DI for a lens, negative image means it's a virtual image in front of the lens. So we know it's a virtual image. And it's in front of your lens. So that means it's going to be over here somewhere. Okay? Great. Now we know where our image is. We know it's going to be virtual. Now we want to figure out the magnification. So remember, magnification is negative DI over DO. So we're going to plug in negative 37.5 divided by 15. So a negative times a negative is a positive. If you put this in a calculator, you're going to get 2.5 as your magnification. So that means that your object is magnified 2.5 times its original size. So what does this mean? Let's look back at our table. 2.5 is greater than 1, so that means our image is going to be larger. And it's positive, so that means our image is going to be upright. Okay, so we have a positive, so our image is upright, and greater than 1, so image is larger, right? We know it's 2.5 times larger, okay? So what we did here is we figured out our focal point and our distance of our object, checking the signs. Then we plugged into our first thin lens equation to figure out the distance of the image. We used the signs to figure out if it was virtual or real and in front of or behind the lens. Then we used our magnification equation and we figured out the sign led us to say whether it would be upright or inverted and larger or smaller. Great. Let's do one more example. This time we'll do an example with a mirror. Okay, so determine where the image will be located and whether it will be real or virtual. Then find the magnification and determine if the image will be larger or smaller and upright or inverted. Okay, let's start. So we're going to start the same way. with our DO. Our distance of our object is at 40 centimeters. And we know DO is always positive. Now, focal point is 15 centimeters. We have a concave mirror, so let's check our table to see if that's positive or negative. Okay, so we have a concave mirror, so that means F is going to be positive. So we're going to keep it as positive 15 centimeters. Now let's use our equation, DI equals DO times F over DO minus F to find where our image will be located. We're going to plug in, we get 40 times 15 divided by 40 minus 15, and we end up with 24. Okay, so what does this mean? Well, we know it's positive. Positive for a mirror. So let's take a look at our table. So for a mirror, our positive image distance means it's a real image in front of the mirror. Okay, real image in front of mirror. Very good, right? So that means it's going to be in front of the mirror somewhere around here. Okay, or it could be over here, but in front of that mirror. All right, now let's figure out what that magnification is. So again, magnification is negative DI over DO. Our DI is negative times 24 divided by DO is 40. Put that in a calculator and you get negative 0.6. So our image is 0.6 times the original size of the object. So what does this mean? Okay, well, we have a negative number and it's less than 1. So let's see, what does that mean? Go back to our table. Negative means the object is inverted or upside down, and less than 1 means the object is smaller. So you have a inverted object that is smaller, an inverted image that is smaller than the object. Okay. So again, what we did here was we figured out our distance of our object at our focal point, and we made sure to check our signs. Then we plugged into our thin lens equation to find the distance of the image. We used the signs to figure out that it was a positive sign, meant it was a real image in front of the mirror. And then we used our magnification equation, and since it was negative, it was inverted, and since it was less than 1, it was smaller. So that means you're going to have a smaller object in front of the mirror that is inverted. So it's going to be 24 centimeters away. So here, smaller, it's going to look like this. Okay? So this is really what you need to know from this section. You need to know how to use the thin lens equation. You need to know how to use this table. You don't have to memorize the table, but you need to know how to use the table. Then you need to know how to magnify, determine the magnification, and how to, again, use this table to figure out if your image would be larger or smaller, upright or inverted. Okay, we did 2 examples together, and tomorrow you're going to do 2 examples on your own as practice problems. Okay. There's also, I want to say at the end of this Apex section, they do a little bit of talking about glasses and how glasses work, and how your retina interprets images. It's kind of interesting, but it's not super important, so I'm not going to test you on it, and I'm not making a video on it. But if you are interested in that, it's slides 11 through 18 in Apex. Okay, so I encourage you to check that out if you are interested, but again, you won't be tested on how glasses work. All right? So be able to use this thin lens equation and magnification equation. And we're going to practice tomorrow. Let me know if you have any questions.